Every hour, a single machine at the edge of a quay moves 10,000 tons of bulk cargo, 166 kilograms every second. Enough to fill an Olympic-sized swimming pool in minutes. That throughput is what makes ship loaders among the most powerful machines on Earth. But sustaining it requires an engineering chain where every subsystem, from a 60-meter lattice boom to the concrete beneath the rails, has zero margin for failure. 10,000 tons per hour is a number that resists easy imagination. To make it tangible, consider the math. That is 166 kilograms of material dropping every single second, roughly the weight of 2 average adults, landing with each tick of a stopwatch. Over the course of a single hour, the loader moves nearly 2,400 cubic meters of iron ore. That volume is almost a perfect match for an Olympic-sized swimming pool, which holds about 2,500 cubic meters. In practical terms, this means the machine could fill or empty a pool of that size in less than 60 minutes, using nothing but a continuous stream of bulk cargo. Scale that up to a full day, and the totals become even more striking. Over 24 hours, a single loader can move 6 million tons, enough to fill more than 250 Olympic pools. At major terminals like Rotterdam's EMO, daily unloading capacities reach 200,000 tons across a fleet, with each high-capacity loader responsible for a significant share of that throughput. In China's Qinhuangdao port, loaders have been measured at just under 9,000 tons per hour, confirming that these figures are not theoretical. They are achieved in real-world operations. Every second, the loader's conveyor belt absorbs a new surge of material, translating raw tonnage into a relentless, measurable flow. This is not just about moving bulk. It is about compressing the work of thousands of people and countless machines into a single, unbroken process. The result is a machine defined not only by its size or complexity, but by the sheer, relentless volume it can handle, turning abstract numbers into a scale of movement that shapes global trade. A shiploader's boom arm stretches up to 60 meters, yet from a distance, the lattice of steel can appear almost fragile, more like scaffolding than a structure expected to move thousands of tons. The secret lies in the geometry of the Warren Truss, a web of interconnected triangles that channels forces along straight lines, minimizing bending and spreading stress efficiently across the boom. Each steel member is engineered to handle axial loads, either tension or compression, so the boom can extend deep over a ship's hold without sagging or buckling, even under a full load. At full reach, the boom faces a moment of about 1,225 kilonewton meters, a force that, left unchecked, would topple the entire machine. Here, the counterweight comes into play. Typically, 30 to 40% of the boom's load is balanced by a massive block of steel and concrete, mounted on rails at the rear of the loader. As the boom extends forward, the counterweight slides backward, precisely matching the shifting center of gravity. This dynamic balancing act is more than a simple seesaw. It's a real-time calculation managed by hydraulic actuators and monitored by sensors embedded throughout the structure. Operators rely on these systems to keep the boom stable while luffing and slewing. Every maneuver is a test of the structure's limits. The steel must never exceed a stress of 210 megapascals, a threshold set well below the yield strength of modern marine-grade alloys. The result is a boom that combines reach and resilience, engineered to flex but never fail, and able to deliver bulk cargo with pinpoint accuracy hour after hour. From the operator's vantage, the boom's apparent delicacy is an illusion. Beneath the lattice, every member and every counterweight is calculated for safety, efficiency, and control. The shiploader's movement across the quay relies on more than brute force. Its 3,000-ton mass glides over concrete thanks to a rail bogie system designed for both strength and finesse. Each bogie features 2 axles, with wheels spaced exactly 1,500 millimeters apart. and a tread width of 260 millimeters. This geometry spreads the load, reducing stress on the rails and minimizing wear even during full-capacity runs. The conical 1 to 20 wheel profile helps the loader self-center, ensuring smooth travel along the dock's gentle curves. Beneath the wheels, a dual-stage hydraulic suspension absorbs shocks. The primary cylinder beneath each axle allows a stroke of 300 to 400 millimeters, cushioning impacts from sudden stops or wind gusts. Secondary elastomeric pads and dampers further diffuse vibrations, shielding both the machine and the quay's reinforced concrete slab. That slab, often rated below 15 megapascals, depends on dense steel reinforcement and neoprene expansion joints to withstand repeated loading cycles. Anchor bolts, set every 1.2 meters and grouted with high-strength epoxy, resist the shifting mass as the loader moves. In the control room, an engineer watches real-time load cell data, ready to adjust hydraulic pressure if a spike appears, perhaps during a storm or a sudden swing of the boom. This vigilance keeps wheel loads near 150 kilonewtons, preserving both the machine's mobility and the dock's integrity. Bulk cargo doesn't just drop into a ship's hold, it moves as a relentless, engineered stream, driven by the loader's conveyor and electric muscle. The heart of this process is a 1.2 meter wide conveyor belt, running at up to 4.5 meters per second. At these speeds, the belt can deliver 4,800 tons of material per hour, with every meter engineered to withstand continuous impact and abrasion. The tension needed to keep this belt moving. A pull of 200 to 250 kilonewtons matches the force required to tow a fully loaded jumbo jet across the tarmac. This raw pulling power comes from dual electric drive units, each rated between 4 and 10 megawatts. These gearless motors operate in parallel, so if one fails, the other can maintain at least 70% of rated throughput, preventing sudden shutdowns and keeping cargo flowing. The Programmable Logic Controller, or PLC, acts as the digital brain, monitoring belt speed, torque, and motor condition in real time. If any sensor detects a fault or overload, the PLC can isolate the problem and command a safe, rapid stop, often in less than 200 milliseconds. Reliability is built into every layer. Mean time between failures for the main drive system now exceeds 10,000 hours, a figure achieved by combining robust mechanical design with continuous digital oversight. The result is a system that transforms the brute force of megawatt-scale motors into a smooth, uninterrupted flow of material, hour after hour, day after day. In this way, the loader's conveyor and electric drive aren't just moving cargo, they're delivering the precision and endurance that global trade demands. The financial scale of a high-capacity ship loader rivals that of a small industrial plant. A single machine can require an initial investment between 15 and 50 million US dollars, depending on its size, drive configuration, and automation level. But the real cost runs far deeper. Over a typical 20-year service life, total ownership, including energy, maintenance, and spare parts, can exceed $100 million. At a port like Headland, where a single loader might move over 6 million tons of iron ore per year, even a few hours of downtime can translate into losses of hundreds of thousands of dollars. For insurance underwriters, these machines are treated as high-risk, high-value assets. Annual premiums often reach 1.5% of the loader's declared value. That means a top-tier loader can cost as much as $750,000 per year just to insure. Underwriters scrutinize engineering data, maintenance logs, and operational records, sometimes offering premium discounts if the operator can prove rigorous safety practices and real-time monitoring. The logic is simple. Every hour the loader sits idle is an hour of lost throughput, delayed ships, and penalties that ripple through the supply chain. In this world, flawless safety and reliability are not just technical goals, they are financial imperatives. At Port Kembla, the investigation team arrived to find the aftermath of a rare but devastating failure. On a day when wind gusts pushed past 30 knots, the ship loader's safety system should have triggered an automatic wind stow, an emergency retraction designed to protect both machine and quay. The loader's anemometer had registered the threshold, but the interlock was manually overridden in an attempt to maintain output. As wind pressures built, the out-of-calibration counterweight failed to balance the boom. A 30-ton section of steel crashed onto the dock, causing $450,000 in direct damages and halting operations for weeks. The port safety officer reviewing the scene noted that the load moment limiter, intended as the final safeguard, had also been bypassed. Official records from insurance claims and port incident logs show that roughly 30% of major ship loader failures can be traced to human error, not mechanical design. In contrast, modern wind stow systems, when left to operate automatically, have prevented damage in more than 95% of high wind events, especially when they operate automatically. The Kembla collapse stands as a cautionary example. When automated safeguards are respected, catastrophic loss is rare. When they're bypassed, even the strongest engineering can be undone in seconds. Every hour, machines like this move more bulk cargo than most cities consume in a day. As global demand rises, their precision and reliability become non-negotiable. The future of trade depends on engineering that never blinks, even when the stakes reach 10,000 tons per hour. Thanks for watching.